and we're going to continue this discussion on modeling and the usefulness of it on projects. So Boshin, can you turn on your video and share your screen? So we're going to talk about this issue of excessive inventory. It's a big problem when taking manufacturing like offsite approach in construction projects. Also detailed knowledge of production operations. So our next presenter, Boshin Zhang, has researched these issues and that could be solved using production system modeling and is here to tell us about his findings. Boshin is a PhD candidate at Stanford, pursuing a degree in civil and environmental engineering with a specialization in sustainable design and construction at the Center for Integrated Facility Engineering. His research focuses on digital twin technologies, supply chain management, and data-driven production process management for industrialized construction. Prior to his academic pursuits, he gained valuable industry experience as an engineer and analyst in leading general contractor firms. His professional background includes working on diverse projects such as commercial developments, hospitals, and entertainment parks. So we're anxious to see what you got for us today. I'll turn it over to you and come back for Q&A. We'll still give you your 20 minutes, so we'll go with that revised schedule.
Yeah, thank you, Gary, and thanks everyone for this great opportunity to present our work here today. So I'm Bo Chen, and this work is done by me and my professor, Martin Fisher. Unfortunately, he's not here today, he's traveling, but I'm gonna present for him. So offsite construction, this particularly offsite modular construction, has been promising to deliver cheaper construction projects by leveraging the benefit of mass manufacturing and economics of scale. But so far, it hasn't delivered that promise despite the decades of practices, as we observed. Today, after we interview with many project engineers and in different general contractor firms, they still believe that the offsite construction, especially for modular construction projects, is more expensive than the traditional project. Here at Stanford Center for Integrated Facility Engineering, or SIFE, we would like to change this. And through this case study, we observed the operational inefficiencies in producing modular bathrooms for commercial and residential projects. And by implementing the production system optimization framework, we were able to identify opportunities to improve the process, and ultimately is to improve the profitability of the project. Right, let's go. So start with a little bit of results from this case study. So after we implement the PSO for this particular modular bathroom factory project teams, we were able to see that we reduced the difference between estimated and actual production lead time from 44% to 4%, in which case we actually get a more close to reality schedule and understanding about the whole production process. And also, we have showed, after we showed all the results, we have showed the opportunities to the factory production team how to increase their throughput by actually 50%. So they were able to have a chance to increase their throughput from producing 4 products per day to 6 products per day. And by synchronizing the offsite production process with the onsite demand to be more just in time. So what we observed is we actually identified opportunities to reduce the inventory investment, the number of products that the factory needs to carry, by 24% to 47%, while still maintaining an acceptable fill rate and achieving the planned completion date. Okay, so the whole research project started from last summer, when we actually went out to observe this modular bathroom factory's process. They invited us to be there to advise. And what we noticed is in their factory stockyard, there's a huge amount of bathroom pods is actually staying there, doing nothing. And some of we look at some of the tags on there, we see some of the pods are actually staying there for over 6 months. So we were so curious, and we actually calculated what's the cost for holding this much of the inventory. So we observed a particular project, which is producing around 450 pots for a commercial project. The average holding time after calculations is around 6 months before these pods can be delivered to the job site. So we only included the opportunity cost and the holding cost for the space. This is already give us a total inventory cost of around 5% of the total contract value. And we are not really considering the cost for the rework that, some of the pods were damaged by the weather over there in Florida. And what's most important is that this inventory cost is not really identified at the beginning of the project, and of course, it's not budgeted, and which means this is going to directly squeeze the profit for the factory, and also this is going to squeeze the profit for the project. We're more curious about why they need to hold on to this much of the inventory and what happened. So we studied the planned production schedule data and a planned delivery schedule. And what we find here, observe 2 points here. First, the production and the on-site demand is pretty smooth. Every week looks like from here, they are producing 20 pots. They are delivering 20 pots to the site. Second, the factory, for some reason, choose to produce all the pots before they start to deliver them. And of course, using this plan data, we can easily see and calculate the factory will see large amount of inventory right before they start deliver to the job site. And this is corresponding to what we actually observed there. So we're even more curious now to understand why. So we actually conduct interviews with the factory managers and factory team, and the results actually reveal that the factory choose to produce early for variabilities in the production process. And also they want to use this much amount of the inventory to accommodate just in case something happened and then the on-site demand changes. And according to them, it's pretty often happens, up to 50% of the time. So as a result, we understand that the factory managers and factory teams understand that both off-site production and the on-site demand are more uncertain than their forecast. So let's look at the actual data. So we also study so this project has done, and then we study their actual production schedule and actual delivery schedule. And from here, as you see, the bars is really having more variabilities than their planning data. And for example, here in the actual delivery schedule, what we see is for a single week, the factory has to deliver 82 pots compared to the 20 pots planned because they have to catch up with the previous week that was 0. But still, if we look at this actual data and compare that to the actual inventory that they were holding, this is still much more inventory that they carried on, and this is much more needed, much more than they needed, which is 82. And of course, holding this much of the inventory is going to cost a lot of money, and as we estimated, that was around 5% of their total contract value. Ideally, we want to, in this case, the factory should be only holding to around 82, 85. Hopefully they know it beforehand, pots. And then we did a quick calculation that's going to save them at least 80% of the inventory cost. So as a summary, this observed problem told us not understanding the variability in offsite production and onsite demand causes costly and unnecessarily high inventory. So the research objective for this project is to reduce offsite construction inventory costs by understanding the impact of variability and synchronizing the offsite production with the onsite demand. Offsite production actually involves key phases. It involves a supply chain here, including the offsite production, storage, transportation, and onsite installation. It is hard to coordinate all these phases because it's hard to predict the variabilities in each of the phases. For the case studied here, because the site and the factory was really close to each other, it was only 1 hour apart, so we mostly focus on the offsite production, storage, and onsite installation. to synchronize the offsite production with onsite demand, and actually start from the project team onsite needs to give a factory about their production schedule and then from there, the factory calculates when they should start to ship the products, how much the storage, how long does it take for them to take the products from the storage, and when they should start to produce and how much they need to produce. And with all this information, they can decide, okay, what is the right amount of the inventory they need to carry with consideration of the variability in each of the phases. We didn't really find a good amount of the knowledge in the current construction management knowledge body. So we actually turned to the operation science principles because this has been used widely by many other industries and to study the interaction between the demand and the production and the variability associated with both. And most importantly, we want to see profitable outcomes for these factories and projects. And also, of course, project production management provides 5 levers for us. And in here, because the product is already designed, by the time we involve, so we mostly focus on the process design, capacity, inventory, and the variability levers to improve the production. So I widely use the inventory policy as this continuous inventory review model from the supply chain management field. This model basically defines a safety stock that the firms or the organizations needs to carry, and defines a reordering point when they see the inventory goes lower than how much they need to start to reorder, and means in our case means the factory needs to start to produce more. And the safety stock is basically defined by saying carry just enough inventory for the demand during the production lead time. So the factory will always have enough products to provide for the onsite. But in order to decide this safety inventory, we also need to understand what is the average and variability of the demand. Also, what is the average and variability of the production time. This variance of replenishment time demand equation actually gave us the answer to combine both. And we can also draw this chart for a trade-off between the inventory investment, how much of the inventory you need to cost in terms of the dollar values, and on x-axis, that's the fill rate. So as we see, the fill in this curve, as the fill rate is approaching to 100%, the inventory investment cost goes to infinity. And this is actually corresponding with our observed problem because the factory wants to fulfill every single possible on-site demand. So they actually choose the fill rate to be 100%. Then they put everything in their inventory. But another important part that this chart actually tells us is if we just reduce the fill rate to be an acceptable level, we can actually save a lot of inventory investment. We can actually save a lot of money by choosing this, by understanding all of this trade-off. Another part also, we need to understand how do we calculate the average for production lead time and the variability of that. And this beautiful equation, Little's law, basically give us an understanding of how do we calculate the cycle time and throughput and working process. The beauty part of this equation is the metrics in this equation is actually leading indicators instead of the lagging ones that sometimes most of the time we use in the construction management. You can basically go out to the floor and calculate and basically just count how many products are currently being under construction. So that's going to be your working process, and also observe how many products is being delivered every day. So that's going to be your throughput, and you get immediately an understanding about the average cycle time for a particular production process. And also the VUT equation, James already explained it very well. In this case, basically tell us that variability of the production lead time comes from 2 parts. First part is the time variability for the products to arrive at a certain workstation, and the second part is the variation of processing the work within this workstation. And this is where basically the factory, the production team can actually improve. And of course, there's also the utilization related to the queuing time, and that's going to be impact directly the overall cycle time because the variability actually creates a queue here. That was looking at just one workstation, but in the real world, the production system is much more complicated. So we need to put all these concepts and data and equation into a process model and use the modeling and simulation tools to actually give us understanding about the whole behavior of the production process. So here in this case study, we took another project as example. This is a university residential building modular bathroom. We actually started from learning about the whole production process and looking at the what we are showing here is looking at the factory floor, but also interview with the factory managers, engineers, and production leaders. We start to map the whole production processes. Even though the factory keeps saying that, every time when they start a new project, they have to reproduce this production flow charts, actual production schedule, production process chart. What we find is typically these offsite modular factories have a pretty robust process with almost at least 85% processes the same. So we are pretty confident that we can actually build a production process system for them. We go on to collect production data for the production modeling analysis. A lot of data the factory is currently collecting, but the quality is pretty bad because there's no quality control and there's no clear understanding how they're going to use the production data. And also some of the data, such as the process rate variation coefficient, the variabilities, they are not really collecting them. And this research and this modeling actually demonstrated how useful they need to collect this data and make sure the data quality is actually good, because it's gonna be garbage in, garbage out. With the map, with the process information, the production data, we went on to use these PSO software to model the production process and estimate the production lead time. The result actually give us a pretty close estimate on the average production lead time, which is 69 days compared to the actual production of 130 bathroom pods for this university residential project. And then compare back to the factory planning baseline, and where they were using the Gantt charts and doing estimates in the beginning of the project. They were estimated for 40 days, which is like 44% difference without considering all these uncertainties and variabilities. And no matter, the factory teams doesn't really trust their planning because they know there will be changes in variabilities. The factory also asked us, could you really look at how we can improve our current productivity, how you can really improve our throughput? And after talking to the factory production team, what we really observe is that each of the team member actually have a different understanding about where is their bottleneck. And by actually showing the capacity utilization chart, we actually give them a visualization with everyone in the same room about, hey, what are the most utilized resources here in your current production process? And we actually identified a painting crew, CNC machine, a wall framing crew. And then immediately after we show this result to the production team, they come up with the recommendations how they're gonna improve. For example, for the painting crew, they immediately decided to change to the new paint. They were hesitating. They don't know if they should focus on this. Now they can actually have something to back them up, and then they can use this new paint for less drying time. CNC machine was pretty close to 100% utilization. The previous understanding was they need to push it to 100%, understand there are variabilities. So even though they they had actually a one more CNC machine, but they are not using it because they want to save the operation cost and all that. Now they understand they need to use it, and they actually have more capacity for this particular couple particular workstations. Lastly, the wall framing crew, after they observe the capacity utilization, they understand how the capacity were used in each of workstation. They reassign some of the labor to the wall framing station, so they actually can balance the whole the resource allocation. So after all of this improvement, we actually did a what-if analysis, and the new result actually showed that we can help them to, or this whole method can help them to improve the throughput from producing 4 per day to 6 per day, and this is already a 50% increase for them, and they were happy about it. Lastly, but not least, the inventory investment analysis. That's what we were trying to focus over here. So as it before showed, the factory choose to have a fill rate of 100%. So again, these numbers are relative numbers. So in this project is $1.4 million. And by having inventory investment for 99%, which is just include the extreme cases, and that already give us an inventory investment reduced to $932,000. Further reducing some of the more extreme cases to reduce the inventory investment for 90%, that gives us a 47% decrease in inventory investment. And this actually triggered this result actually triggered a conversation between the production team and the on-site project team to say, hey, could you actually make sure while you're planning for installation that the on-site demand can be pretty smooth and don't always give me the last time changes. And because that's cost us a lot of money, and eventually this money goes to you. So by showing these results, we can actually see that the project team, the factory team will work together trying to reduce around, if they can reduce 50% of the on-site demand variability, this also helps the project to reduce 24% inventory investment. So as a conclusion, this project actually, after implementing PSO on this project, I really designed the production process from a systematic perspective. This enabled a better understanding about the impact of variability in the offsite production duration forecast. It's enabled visualization of data, visualization of and support a data-driven strategic allocation of the capacity within the offsite production. And also, lastly but not least, enabled to reduce the inventory investment while still maintaining an accessible fill rate and achieving the project target time. All right. So yeah, that's all. Open for any questions.
Very interesting work to show the power of production system modeling on changing the bottom line. Had a good question for you. This is a very hard sell to project teams, as traditionally superintendents like to be able to see lots of modules on site. Is there a way to easily show them how much excess inventory is costing?
So yeah. So in our case is the inventory investment, the amount of money that is showing. So the inventory investment is actually representing, in our case study, the amount of the modules that the factory needs to accumulate before they can actually be delivered to the job site. By saying deliver to the job site actually doesn't have a laid down area. So they have to actually immediately put the modules inside. Therefore, the amount of the inventory investment is already showing how much of the cost that the factory has to tie. But also at the beginning, we actually calculated the cost for holding this inventory. That's going to be a lot of money as well. Because there will be people doing the handling, there will be security costs, there will be also the damages due to when they move around all these pods. So all of this money, once they put together a number and show it to the superintendent changed their mind immediately.
Interesting.
So they decided not to accumulate that much amount of the inventory. And also, interestingly, we showed this number. Communicated this number to the owner, because the owner's contract is actually encouraging the factory and project team to produce more. to
Mm.
produce more modules on site. But then after they seeing how much the cost for holding this much of the inventory, they decided, no, this is not the case. We're not going to do that. Please coordinate with the offsite factory. Please coordinate between the project team and the factory team. Don't produce that much. Just produce enough.
So I was wondering how the company responded to your optimization results. It sounds like they actually implemented what they could at the time.
Yep. Yep. So very interesting response. The first response from the factory manager was, "Oh, we should actually hire those process engineers back because during the COVID there was a cash flow crisis, so they fired the whole process team." And they were counting on the superintendents and the production floor managers to really understand about all these flows and processes in operation science. But immediately they see the value for designing the production process, designing production system. So yep, so they immediately want to really have professionals helping them.
Yeah, excellent. I've got the questions rolling in here. Are there differences if the pods factory is part of the vertical integration with the GC or if it's not?
So yes, it will be different. In our case study, what we see is it is a vertically integrated modular factory. So the general contractor and the modular factory, it's the same company. But what to see is interesting that once it's vertically integrated, the factory is trying to accommodate because they said, oh, we are the same company, we should be on the same team, so we should accommodate everything they ask us because they're going to be the big daddy for us. But this actually created this whole inventory problem because they're starting to accumulate all these and they're trying to make sure every single request from the project team they can fulfill. But versus if it is not vertically integrated, this factory is also taking on projects from other general contractors. They said, oh, they can negotiate. If they have too much about their demand, then we're gonna fulfill them.
Yeah.
So it's actually make a difference.
So another question for you here, is the cost of inventory usually included in the bid of the manufacturer before the project is awarded? Business-wise, would it make sense to include this cost within the bid?
So yeah, the factory decided to include this cost now. Before they didn't really recognize it. They thought, $250 per pod per month, that's enough for us. But they didn't realize that there's how much amount of the inventory cost for holding those inventories.
Yeah.
So yeah.
So let's see, another question here for you, and probably one, we'll have to wrap it up after this. Is the ideal inventory practical? There are risks that have to be accounted for. How does hindsight play into your analysis? How would you share this to future production managers with practical risks?
Yeah. So it's really hard. The short answer is really hard to have the factory managers believe that they only need this much amount of inventory for just enough. But the cost part is really making the difference as we're showing the trade-off, we're showing the cost. They understand that they need to make at least some changes. So instead of really going into the ideal, they said, okay, let's reduce it to, like, for example, 2/3 of the original inventory amount, and let's see if the cost went down, and let's see if we still can achieve our targets.
So take a baby step or take a step towards that.
Exactly.
And see what happens before they
yes.
go whole hog and get to the a more ideal level, let's put it that way.
Correct.
Good idea. All right. Well, thank you for your hard work and analysis, and very insightful. Look forward to reading the paper.